now go to the next module, which is the perceptron learning algorithm. And we'll now see a more principled approach of learning these weights and threshold. But before that, we'll just again revisit our movie example and make it slightly more complicated. Now here, what the situation is that we're given a list of M movies and a class associated with each movie indicating whether we like the movie or not. Right? So now we have given some data of the past M movies that we have seen and whether we like this movie or not. And now instead of just 3 variables, we have these N different variables based on which we are making decisions. And notice that some of these variables are real, right? They are not Boolean anymore. Right? The rating could be any real number between 0 to 1. Okay? And now based on this data, what do we want the perceptron to do actually? So I've given you some data, these factors. I've also given you the label 1 and 0. So if the perceptron, if I tell you, okay, my perceptron has now learned properly, what would you expect it to do? Perfect match, right? So whenever I feed it one of these movies, it should give me the same label as was there in my data, right? And again, there are some movies for which I have a label 1, which are positive, some movies which I have a label 0. So I'm once again looking to separate the positives from the negatives, right? So it should adjust the weights in such a way that I should be able to separate, right? So that's the learning problem that we are interested in, okay? So now with that, I'll give you the algorithm. Okay, this is the perceptron learning algorithm. We have certain positive inputs which had the label 1. We have certain negative inputs which had the label 0. And now I don't know what the weights are, right? I have no prior knowledge of what the weights are going to be. I need to learn them from the data. So what I'm going to do is I'm just going to initialize these weights randomly. Right? So I'm just going to pick up some random values for this. So this should be small n. So this should be small n. And now here's the algorithm. While not convergence, do something. So before I tell you what to do, can you tell me what is meant by convergence? When will you say that it has converged? When it is not making any more errors on the training data, right? Okay, or its predictions are not changing on the training data. So that's the definition of convergence. Okay. Now here's the algorithm. I pick up a random point from my data, which could either be positive or negative, right? So it comes from the union of positive and negative, basically all the data that I have. I pick up a random point from there. If the point is positive, right, and this is the condition which happens, what does this tell me? If the point was positive, what did I actually want? Greater than 0. But the condition is less than 0. That means I made an error. So I've made an error, then I'll just add x to w. I see a lot of thoughtful nodding. I hope you're understanding what is happening. Let's see. So what is w actually? A dimensional? N dimensional. N plus 1, right? Because w naught is also inside there. So actually there should be w naught also here. Right? And what is x? Again n dimensional, right? And that's why this addition is valid. So let's understand that the w and x both are n dimensional. Okay. Now let's look at the other if condition. Can you guess what the other if condition is? If x belongs to n and summation is greater than or equal to 0, then, okay, so that means you've completely understood how this algorithm works. Because that's right. So now consider two vectors w and x. So remember what we're trying to prove is, or get an intuition, not prove actually, get an intuition for why this works. Okay. So we'll consider two vectors w and x, and this is what my vectors look like. Very similar to the case that we are considering, w0 to wn and 1 to n. So this again, x naught is just 1, right? Okay. Now this condition that I've been talking about, it's nothing but the dot product. Right? How many of you have gone through the prerequisites for today's lecture? Okay, good. So it's just the dot product, okay? Now we can just rewrite the perceptron rule as this. Instead of the dot product, instead of using that summation thing, we can just say that it's a dot product. Okay. Now we are interested in finding the line w transpose x equal to 0. So that's our decision boundary, right? Which divides the input into two halves. Okay. Now every point on this line satisfies the equation w transpose x equal to 0. What does that mean actually? Yeah. So just a simple example is that if I have the line x1 plus x2 equal to 0, then all the points which lie on the line satisfy this equation, right? So you could have 1 minus 1, 2 minus 2 and so on, but 2 comma 2 cannot be a point on this line, right? Every point lying on this line satisfies this equation. So every point lying on this line actually satisfies the equation w transpose x equal to 0. So that, can you tell me what is the angle between W and any point on this line? How many of you say perpendicular? Okay, why? Dot product is 0, right? So if their dot product is 0, they are orthogonal, right? So that means if I take this line, then my vector W is orthogonal to this, it's orthogonal to this point, to this point, to this point, to every point on the line, which is just the same as saying that the vector is perpendicular to the line itself, right? As simple as that. So the angle is 90 degrees because the dot product gives you the cos alpha, and that is 0, right? And since it's perpendicular, as I said, to every point of the line, it's just perpendicular to the line itself, right? So this is what the geometric interpretation looks like. This is our decision boundary, W transpose X, and the vector W is actually orthogonal to this line. Okay? That's exactly the intuition that we have built so far. Okay? Now let us consider some points which are supposed to lie in the positive half space of this line, right? That means these are the points for which the output is actually 1. Okay? Now, can you tell me what is the angle between any of these points and W? Oh, you guys are actually trying to tell me the angle? You've got some measuring stuff? No, so I'll give you 3 options. Equal to 90, greater than 90, less than 90. Less than 90. It's obvious from the figure, right? Now, if I take any point which lies in the negative half space, what is the angle going to be between them? Greater than 90, right? Again, obvious. And it also follows from the fact that cos alpha is W transpose X by something, and we know that for the positive points, W transpose X is greater than or equal to 0, right? That means cos alpha would be greater than or equal to 0. That means the angle alpha would be less than 90 degrees. And for the negative points, W transpose X is actually less than 0. That means cos alpha would be less than 0. That means alpha would be greater than 90 degrees, right? So it actually follows from the formula itself, but it's also clear from the figure. So keeping this picture in mind, let us revisit the algorithm. Okay. So this is the algorithm. Okay. Now let's look at the first condition, which was this. Now if X belongs to P and W transpose X is less than 0, then it means that the angle between X and the current W is actually greater than 90 degrees. But what do we want it to be? Less than 90 degrees. And our solution to do this is, but we still don't know why this works. Now anyone knows why this works? Okay, so let's see why this works. Okay, so what's the new cos alpha going to be? It's going to be proportional to this, right? It's going to be proportional to this. I'll just substitute what W nu is. Fine. That means if cos alpha nu is going to be greater than cos alpha, what is alpha nu going to be? Less than, and that's exactly what we wanted. This angle was actually greater than 90 degrees. So we want to slowly move it such that it becomes less than 90 degrees. It's not going to get solved in one iteration, right? That's why till convergence. So we'll keep doing this. We'll keep picking the x's again and again till it reaches convergence. That means till we are satisfied with that condition, right? Now let's look at the other condition. X belongs to n and W transpose X was greater than or equal to 0. Then it means that the angle alpha is actually less than 90 degrees, and we want it to be the opposite. Okay, I'll just quickly skim over this. W minus this, X, right? Okay, I forgot to mention that this is actually a positive quantity, right? I mean that's why that result holds. Okay, that means cos alpha nu is going to be less than cos alpha, and this slight bit of mathematical incorrectness I'm doing here, but that does not affect the final result. So I'll just gloss over that, and you can go home and figure it out. But still the final, it doesn't take away from the final intuition and interpretation, right? And so now the new cos alpha is going to be less than the original cos alpha. That means the angle is going to be greater, and that's exactly what we wanted. Okay. So we'll now see this algorithm in action for a toy data set. So this is the toy data set we have, and we have initialized W to a random value, and that turns out to be this, right? I just picked up some random value for W and ended up with this particular configuration for W. Okay. Now we observe that currently W transpose X is less than 0 for all the positive points, and is actually greater than or equal to 0 for all the negative points. If you don't understand W transpose X, it's just that all the positive angle points actually have a greater than 90-degree angle, and all the negative points actually have a less than 90-degree angle. So this is exactly opposite of the situation that we want. And now from here on, we want to actually run the Perceptron algorithm, right, and try to fix this W. And how does it work? Remember, we randomly pick a point, okay? So say we pick the point P1. Do we need to apply a correction? Yes. Why? Because it's a positive point and the condition is violated, right? So now we add W equal to W plus X and we get this new W. So notice that we have a new W, okay? We again repeat this. We again pick a new point and this time we have picked P2. Do we need a correction? At least from the figure it looks like the angle is greater than 90, right? So we'll again do a correction. We'll add W is equal to W plus P, right? This X is actually, sorry, P2, and this is where we end up, okay? Now again we pick a point randomly, N1. Do we need a correction? So this is what our W is, this line here, and N1, right? So we need a correction, okay? Now what is the correction going to be? Minus. And then the W changes, okay? Now we pick another point N3. Do we need a correction? No, at least from the figure it seems like the angle is greater than 90. And we continue this, right? For N2 we don't need a correction. Now for P3 again we don't need a correction. The angle looks less than 90. Oh sorry, actually we need a correction. The angle is slightly greater than 90. And this is our correction, okay? And now we keep cycling, and now as I keep cycling over the points, I realize that I no longer need any correction, and it should be obvious from the figure that for this particular value of W, now all my positive points are making an angle less than 90, and all my negative points are actually making an angle greater than 90. That means, by definition, now my algorithm has converged, right? So I can just stop it. So I can just make one pass over the data. If nothing changes, I'll just say it has converged, okay? Now, does anyone see a problem with this? It will never converge in some cases. So can someone tell me why? Yeah, we are considering only the cases where the data is linearly separable, right? That we already assumed. So what you're trying to tell me is that you're going over these points cyclically. So let me just rephrase and put words in your mouth. That what you're trying to tell me actually is that I take a point, I adjust the W. But now for the next point, I maybe go back to the same W because that point asks me to move it again. And I keep doing this again and again and basically end up nowhere, right? And that's why this will never converge. That's exactly what you're trying to tell me, right? Or that's exactly what I'm forcing you to tell me. So that's not the case, right? This algorithm will converge.